Hello, everyone. My name is Hailong Sun. I am a PhD candidate in operations research at National University of Singapore. So today I'm going to talk about a convex optimization for bundle size pricing problem. So basically, we propose an efficient method to solve a difficult stochastic optimization problem called bundle size pricing. This is a joint work with my advisors, Xiaobo and Piaw. Okay, here's the plan of this talk. I will first motivate the problem, and then formally define what is the bundle size pricing problem. And then I will propose our solution approach and looking at the numerical results, and finally conclude this talk. Okay, so let me start by introducing what is the so-called bundle size pricing problem and why we are looking at this problem. So let's consider a multi-product firm selling bundles of products, and customers can select their preferred bundles. So the price of the selected bundle only depends on the size, namely the number of products within the bundle. For example, suppose we have 3 products, then we only need to set 3 prices for bundle size 1, which is just the price of the individual product, and for bundle size 2, price for any combination of 2 products, and for size 3, just all the products. So let's look at a particular example. So this is a movie card launched by Golden Village, which is a Singapore-based company operating a number of movie theaters. You can buy this card with a discounted price and watch any 10 movies you like with this card. And you can see that the unit price for each movie is actually lower than if you purchase separately. Yet another example is the subscription to magazines, for example, The Economist. So in this figure, you can see that you have 3 options to choose. And the price of each of them depends only on volume of magazines included. So actually, you can get lower price per week if you choose to buy a larger size of bundle. And actually, you can see that the per week price of a 2-year bundle is lower than the half-year bundle by more than $1. So this is the bundle size pricing. Okay, so now we have seen that the pricing mechanism looks very simple. However, if you try to optimize the bundle size pricing problem, you will find that it is very difficult. Okay, next let's look at the formal definition of the BSP problem. So consider a multi-product firm offers a set of bundles. The bundle size is denoted by set capital S. Customer valuations of per items is denoted by this vector tilde U, and we denote the distribution of tilde U by F. We assume that the valuation for offset option is 0. So the firm sets price Pi for bundle of size I, and we assume that the valuations for items are additive. Namely, the valuation of a bundle is just the sum of individual products. And we assume that customers have unit demand for each item. Namely, the customer will at most purchase 1 unit of each product. And finally, we normalize the population to just 1. Okay, this is the basic setup. So let's look at the customer's problem. The customer selects products to maximize utility surplus. So here we denote the ith order statistics as tilde U bracket I. So it is just the ith smallest value in the vector U. So given this tilde U, the valuation for bundle size J is just given by this expression, and we simply sum over the largest value J products, which is in fact the partial sum of order statistics. So the expected demand for bundle size I is just the probability of choosing this size, which is given by this probability. Here we can see that G, the valuation, omega is the valuation for bundles, and G is the joint distribution of this valuation. you should know that this distribution G is different from the valuation distribution F, which is for the products. Okay, next, let's look at the firm's problem. So the firm simply set prices of bundles to maximize profit. Here, the decision variable is the negative price vector, and the profit is just the price minus the cost times the expected demand, and then we just sum over all the bundle sizes. So here we assume that the cost of offering bundle size I is homogeneous. Namely, so this is typically the case for most applications of PSP. And so Qi star of P is just the induced expected demand for bundle of size I, given price P. So now you can see that the main difficulties include the following. So first is it is generally very difficult to directly characterize G, which is the distribution of the partial sum of order statistics. And also it's difficult to compute the expected demand under G. So more importantly, solving the profit maximization problem is very challenging because it might be non-convex. So we don't even have a closed form expression of the objective function. So here we may not know the explicit form of Qi star. Okay, so next let's look at several existing approaches for this problem. So here we only select the most relevant papers from the optimization perspective. The first one uses simulation optimization method, which is a black box optimization algorithm to compute prices. So this is proposed by Chung et al. In 2011 and published in the American Economic Review. Basically, they first calculate demand for each bundle using simulation, and then they can simulate profit for any price vector, and finally they can solve the resulting nonlinear program using a sequential quadratic programming algorithm, possibly with one star. So actually the approach is very general for any given distribution, but the concept is also very clear. It can get stuck at some local optimal, and it is actually not scalable for a relatively large number of products. So another approach is the asymptotic heuristic proposed by Abdallah in 2019. The paper is just accepted in operations research. Basically, they analyze the so-called asymptotic regime where number of products goes to infinity. And based on the analysis, they can design closed-form pricing rules, which have very good performance for large-scale problems. The pros is that their simple pricing rules are very easy to implement and is suitable for large-scale problems. But actually, the cons is that it can be far from optimal for small-scale problems. So later we will see this in the numerical experiment. Okay, so next, let me introduce our approach. So the main idea is the following. Notice that although we don't know the distribution G, but actually we can easily get unbiased estimate of the mean and covariance matrix of G by simulation. So this is fairly simple, since we only need to draw enough samples from distribution F, the distribution for products. And then we can sort the values and calculate the partial sums. And then we can get the empirical estimates of the moments. So actually, this is possible because of a very crucial property of the bundle size pricing problem. Namely, so the choice of products for each size of bundle doesn't depend on the price you set. Because whatever price you set, customers will always choose the most valued products for each size of bundle. So in this way, we can incorporate the moment information to a class of a discrete choice model called cross-moment model. So this model is introduced by Mishra et al. In 2012. So we can actually try to solve the PSP problem under this cross-moment model. Okay, so before introduce our main result, let me first introduce this cross-moment model briefly. So the CMM is just basically we solve this upper bound of the expected value of customers' utility maximization problem. Here, capital theta is the set of distributions with fixed mean and covariance matrix. So here, if we drop the superminimum here and put some parametric assumptions on theta, on small theta, then we actually can arrive at some random utility choice model. For example, the multinomial choice model or the multinomial logic model or probability model. So here we actually relax the parametric assumption, and instead we find an extremal distribution with given moments. Then we can actually build a surrogate demand model based on the choice probability under this extremal distribution, which optimize this problem. Okay, so after getting this surrogate demand model, we can present our main result. So first, we show that the band of demand, which is the choice probability under CMM, is actually given by the optimal solution to a strongly concave maximization problem. So here we are maximizing a linear function of Q of X, which is the choice probability, plus some regularization term. So here, omega is the mean vector of the bundle valuation, and P is just the price vector, and X is the choice probability, and so delta is the unit simplex, and sigma, capital sigma, is the covariance matrix of omega. So with this result, we can further show that there exists a one-to-one mapping between the price vector and the choice probability vector. So with this one-to-one correspondence, next, we are able to show that the profit maximization problem can actually be written as this form, with the choice probability as a decision variable. And then we can show that the profit optimization problem with choice probability as decision variable is actually concave, which is very helpful in solving the BSP problem, because now if the problem is concave, then we can simply solve this problem using conventional solvers. For example, we can use Epmicon in MATLAB to solve this problem readily. And you can also design some first order algorithm yourself. So basically, this formulation is very flexible in handling any market share constraint. For example, you can just put some linear constraint on this Q, and also you can select a subset of the bundle sizes. Namely, you can incorporate the bundle size constraint. And also, we found that this problem can be scalable to a large number of products. So the natural question is, what about the performance of this approach? So next, let's look at some numerical results. So first, we compare our approach with the simulation optimization approach. We test several common distributions. For example, the exponential, uniform, logit, independent normal, and normal with correlations. So we test several number of products, namely 3, 4, and 5. So we can see that the simulation optimization approach can get near optimal solution for small scale problem. And the profit of our approach is quite near to their approach. So in this case, it means that the CMM approach can get near optimal solution. So we also compare our approach with the asymptotic heuristic by Abdallah. So here, we vary the number of products from 3 to 1,000. And we also consider 5 common distributions, which is the same setup with their experiment. So this is the box plot of the ratio of the out-of-sample profit of CMM to their approach. So here, if the ratio is greater than 1, then it means that our approach attains more profit. So you can see that in almost all cases, our approach produced higher profits. So in particular, for small-scale problems, this advantage is more significant. So as the number of products grows larger, the two approaches actually get closer and closer. So this is because they already proved that in the asymptotic region, their approach is optimal. But here we show that if the number of products is small, our approach performs better. So we also compared with their approach for the single size pricing policy. So single size pricing policy simply offer only one size of bundle. In fact, solving a single size BSP under CMM is quite straightforward. It actually reduces to a single dimensional root funding problem. So here we vary the number of products from 3 to 100. And you can see that our approach still outperforms theirs. Okay, so now let me conclude this talk. So the key takeaways are the following. So first, we can use cross movement to capture the correlation structure of the BSP problem. The second, using two moments, we can actually construct convex approximation to the original BSP problem. And third, so I think that this approach is very promising to handle other bundle pricing problems. For example, the mixed bundling problem. So in fact, a more interesting case is what we call the partial mixed bundling problem, where instead of considering all the possible bundles, we only price a few bundles. So this problem is more challenging than others, since it involves price constraint, which is very hard to deal with. So in the future works, we would like to consider, for example, proving some performance guarantee or incorporating the price constraint. And also here is an ongoing project, which is the bundle recommendation in online setting. So, okay, I will stop here. So thank you for your attention.